Hello, everyone. Thank you so much for joining this webinar today. My name is Allie Yamagata from Saint-Gobain of America, and I'm the YPN liaison for the Cements Division, and I'll be your host for today's webinar. Before I start, I'm going to quickly announce the next 16 Advancing Cement-Based Materials Conference. Please save the date of June 10 to 12, 2026, which will be held in Miami. We have our agenda for the next webinars. On February 3rd, we're having another webinar with Dr. Cesar Hormano. Make sure you sign up for that. We're going to send an email in the next few days. For those who are not familiar with ACerS, I want to quickly talk about ACerS and the benefits of being a member. Being a member of ACerS gives you access to resources that allow you to continue to learn and grow, gain recognitions with awards and scholarships, apply to support to travel and attend conferences. And this is the membership path, depending on where you are in your career. If you're students, we have the Material Advantage Student Program, graduate researcher. We have the associate membership. If you're a professional, I've never been involved in ACerS, you can join us for free for a year and then have a second year for reduced costs. And after that would be the individual membership. Be aware that the prices are being adjusted in 2026. And one of my favorite things from ACerS that is available for members is the mentorship program for students, professionals, and faculty. And it's a really great program where you'll be like matched. If you're, let's say, if you're like a young faculty, you can be matched with a senior faculty and help have this mentorship. The deadline to sign up was extended and it's currently open for sign up until January 19th. So make sure you sign up before that. Um, this webinar is brought to you by the Cements Division. So what is the Cement Division? It's one of the 11 divisions of the American Ceramic Society, which advances the fundamental material science of cement, which with an emphasis on nano to microscale research and develop new technologies for concrete. There's opportunities to connect, meetings and event, resources, leadership developing opportunities and awards. Uh, every year we organize our annual meeting, Advancing Cement Materials meeting. Next year it will happen again June 10 to 12. I hope to see you all there. We're currently open for sponsorships. So you can check our conference page for the flyer, but if you need more information, please contact Vicki Evans and Pranoy Suriname. Now I would like to introduce today's speakers, Professor Nishant. He's an associate professor in the Department of Civil and Environmental Engineer at the University of Illinois Urbana-Champaign. At Illinois, his research group focuses on the chemistry of construction materials using advanced characterization techniques. His research efforts have been recognized by numerous awards, including 2021 Stephen Brunner Award and 2025 Early Career Award from the American Ceramic Society and the 2025 Dean's Award for Excellence in Research at Illinois. During this talk, we will have a Q&A session after each part of the talk, but feel free to submit your question during the presentation on the Q&A box. And there is a box there in Zoom, and we will look at during the Q&A session. Now it's a great honor to give the floor for Professor Nishant.
Okay, thank you so much, Alessandra, for this very nice and warm introduction. So I'm going to go ahead and share my slides here. Okay, Alessandra, can you confirm if you can see my slides in the full screen view?
Yes, I can see your slides, yes.
Okay, all right. Well, welcome everybody to this webinar. I'm Nishant Garg. I'm an associate professor here at University of Illinois. And I'm going to talk about accelerating and automating the testing of cement-based materials. So it's good to see everybody here. And one of the things I discussed with the organizers here is that I want to keep this webinar pretty interactive. So if you have questions as I'm presenting, feel free to put them in the chat and I'll try to answer them as we go. I'll also take some pauses throughout my talk. I have a couple of different sections to take questions focused on each one. So that way it's not a one-way monologue. So just feel free to ask your questions as we go. Okay, so let's start with a very broad introduction here. And I think in terms of questions, yeah, Alessandra, I'm not sure if I'll be able to see them. If you have any things come up, just pause me and I can answer and I can take them. Okay. So in terms of the very broad introduction, I want to start off with, why should we care about accelerated testing? Why don't we kind of live with, what we already have? So I'll start off here, with a lighter note. I know there's a lot of students here, and the best way to communicate with students is through memes, and that's what I've, learned over the past few years. So if you consider this one in this situation, many people may have been in the past, and certainly I think I can say I've been at some points where, your spouse is thinking, I bet he's thinking about other women. And then what you are thinking is, well, how can I accelerate the testing of my concrete so I can save time and money, right? So there's a disconnect between what the two people are thinking. But really, the idea here is that we can save both time and money if we accelerate the testing. Let's go a little bit deeper into that for a moment. So people say time is money, but what I'm going to argue here is that time is actually more than money. In fact, it's way more valuable than money is. And here's the reason. If you think about money is in principle just capital, materials, and labor, and in principle can be scaled up. If we consider time, it's a really scarce resource. Well, if we consider our universe, the universe that you and I, all of us inhabit, it has about 10 raised to about 22 stars. So all of these are essentially, let's say, free, nuclear reactors in the sky, which we can harvest the energy. If we build all these Dyson spheres, and there's no shortage of mineral reserves on many of these rocky bodies. So we can harvest that more and more. We have been doing that, this kind of harvesting of resources over the past few hundred years with automation. But moving forward with robotics and AI, this will only increase quite in an exponential format. So you can imagine that the cost of accessing these things will radically come down. And by the year 3000, we should have multiple colonies across and beyond the solar system, right? We usually think of in the time frame of a few years, maybe 5 year or 10 year or 2050, but I like to think in a kind of longer time horizon. So by the year 3000, you can imagine a very, very material abundant world. However, time is still continues to be a limited resource, and I'm not sure if there's any change in that pending any breakthrough in immortality, right? So there's no elves inside. If you know any elves, please let me know, but we are still limited by the human lifespan. There's also no time machine yet, right? The principle of physics do not allow for any such thing to exist yet. So if something gets invented in the future, that's a different thing. But for now, we are very much limited. So in summary, you can imagine that more and more of our factories, of our plants, you can imagine a cement plant or concrete plant being more and more automated and maybe potentially run by some of these humanoid robots that are coming in the market. You need maybe 100 people to run a plant. Maybe you can run this with actually a few humanoid robots. So that will bring the cost of some of these things very, very down. On that note, if you consider some of the major companies that are into this, they also happen to have a strong connection, or are car companies. For example, Tesla is a car company, but it's also now getting into humanoid robots with the Optimus. If we consider Figure, that has close collaboration with some of the German car makers. If we consider Boston Dynamics, they have a huge backing from Hyundai, which is another car company. So you can imagine that some of these humanoid robots will come at scale, given that the car companies are now very much interested in them. On the other hand, we don't have any elves in sight, so this long age and immortality is still going to be very, very far away until something happens. Okay, so that being said, the acceleration and automation is going to happen, and we figure out how we can do it. And what I'm going to talk about in today's talk is 3 different areas where we have applied some of these ideas, and they're broken down into particle analysis, reactivity, and sorptivity. And I'm going to pause after each section to see if there's any questions. But let's start with the particle analysis, because if you consider cements, these are really, we're talking about these particles. So this is the work we started with my first PhD student, Krishna, who graduated last year, and now he's working with the Federal Highway. And we started to look into particle analysis of cementitious materials. If you consider concrete ingredients, you can see that essentially cement is the most expensive and CO2 intensive component. And then you have other usual suspects such as the fine aggregate, coarse aggregate, water and mixtures, and you mix all of these together to make the most used material on our planet. After water, this beautiful material we call concrete. And one of the things that has been happening over the past few decades is we replace cement with SCM due to many reasons, right? To cut down the cost, to improve the durability, to improve the long-term performance, and also increasingly now to reduce the CO2 footprint. There has been a huge interest in SCMs. And while there has been these standard SCMs, mostly slag and fly ash, in the western part of the world, some of these industries are declining. Specifically, coal production is being replaced by, for example, natural gas and other energy sources. So fly ash is not there as much as it used to be. However, this story is slightly different in the eastern part of the world, where the fly ash and coal production is actually going to grow. But in certain parts of the world, let's say in the western side, the fly ash is going to decline. And then there are new SCMs that are coming on the market, and there's a whole range of them. There's calcine clays. So I did my PhD on calcine clays, and this is a very much of a material which is getting a lot of attention. There's natural pozzolans. They have been around for a long time, but now there's a renewed interest in these materials. And then, of course, there's the idea of harvesting the ashes, taking them out from the landfill, as well as any other industrial residues, could be any slag residues, and so on. The point of the matter is, all of these ingredients are very complex phase assemblages. They are very much a mixture of many different things, very complex. So what we wanted to ask with this question was, if you consider a cement chemist who has just, graduated from university, and she's having a couple of thoughts in her mind. She's got XRF, XRD, and SCM for chemical information. She can get the physical information by PSD and BED. She can do calorimetry for kinetics. And then one of the techniques we have been very much interested to look at the particle analysis is Raman imaging. And this is a very natural question. What can you use Raman imaging for? And the argument I make here is that, the relationship that XRD has to XRF, Raman has to SCM. As in, XRF gives you bulk chemical composition information, XRD gives you mineralogical information. Similarly, SCM gives you elemental maps, and Raman gives you mineral maps. So combined together, they're very powerful and give a comprehensive picture of any powder we are looking at. By the way, that's not a real cement chemist. That was an AI-generated chemist, just for that. Just to let you know. Now, in terms of the analyst toolkit, there's many tools an analyst can use. And right now, let's say Raman imaging is not inside this toolkit. And one of the things we have been exploring in my lab over the past few years, if this can be a potential tool that can be useful for analyzing the materials we care about. So over the years, we have explored many different applications of Raman imaging, all the way from static systems, which are systems that, let's say, don't move or change, to dynamic systems which change over time. And some of these I'm going to cover over the next few slides. So also on a lighter note, people ask, what is Raman imaging? I would say if you were to compare Raman spectroscopy and Raman imaging, this will be different. It's a slightly refined version of the original method. But maybe let me go a little bit more how Raman imaging can give you things that are not possible with a simple optical imaging. So this is an optical image of a granite particle, of a granite piece of rock. And if you collect spectra in a grid-like fashion on this system, you get these many different patterns, which you then analyze and split into different components. And once you do that, you can now get a spatial distribution of all the phases that are present in this system. So essentially, if you had over here a particular phase, now it is color coded based on the pattern that is a fingerprint of that particular mineral. So now we can do that. And this kind of thing is actually routinely done by many other industries. So here's an example I'm going to blow up. And this is actually a time for a question for the audience. So the question here is, this is a material in which Raman imaging has been done. Can you guess what kind of material is this? And I will give you a hint. I can bet that many of you have put this material or a very similar kind of material in your mouth at some point in your life. So go ahead to write in the chat, what do you think, what material is this?
I think it can be sometimes a little bit confusing, Zoom, because the Q&A is separate from the actual chat. So if you guys want to send like messages, you have to use the Q&A box. It's a little weird, confusing. And Carolyn Premiers, I don't know Professor Nishant, if you saw it, she sent like Anasing.
Yeah. Yeah. So for some reason, I'm not able to see the chat on my end. So I think I'll just rely on you to tell
Yeah,
me. But
okay.
oh, I can see it under the Q&A part
Yeah.
now. Okay, I see. Yeah. So again, I think this is close, Caroline. So it's essentially this is Excedrin. So there's the over-the-counter painkiller and kind of fever reducer. So you can see that it has all the usual components, right? It has the aspirin, it has the acetaminophen, which is Tylenol, and it has the caffeine. And now you can imagine that if you're somebody like me, and sometimes I'm trying to save money, and I would just break the tablet in half, and if they had some bad quality control and all the caffeine was on one side of the tablet, I'll just get high on caffeine. I will not get any of the medicine that I really need, which is aspirin or Tylenol. So this is a cross section of a pharmaceutical pill, and the pharmaceutical industry already uses this to do the quality control, to see and to quantify what ingredients are present at what proportions, and also what's the spatial distribution of all these ingredients. And we wanted to see if we can do the same thing with Raman imaging. And what we find out here, let me give 1 second. And we made these little pills of ordinary Portland cement, where we are able to then quantify almost all the phases that are present in it. These are largely crystalline. And then when we compare the quantification with the gold standard techniques such as X-ray diffraction, we get a decent correlation. And that really, I think the nice thing with Raman is that now you can start to see individual grains of these minerals at a very, very high resolution, right? In principle, you can do the same thing with SEM EDS, and there has been a lot of good work done over that over the past few decades, starting from NIST. And the idea, but here is it becomes highly complementary because now instead of relying on the elements and to come up with a mineral stoichiometry, you can directly map the mineral as well as the polymorphs. So then you can see, do this thing where you have individual mineral maps of all the phases, even something like quartz, which is an impurity in this system, it's present in 1%, and you can see that, right? And one of the key things we can get here quantitative is that we have a statistically significant number of points that we have done the point counting on. So if you consider each of these image, it has about 250,000 pixels in it. So it's a really large amount of data. And it is made by stitching together many small images to get a large enough image. So I joke to my students that they really have become, tailors. All they do is they just stitch images together all the time. Okay, time for maybe another quick quiz. Can anybody identify what phase is this? Okay, so maybe I will kind of reveal the answer here. This is actually not a phase. This is actually an iPhone photo of the night sky that my student took. And you can see it's kind of very similar to what astronomers do. They are counting at the white pixels and they look at the stars. And you can see the scale is a little bit different, but they look at the stars in the sky. We look in the stars of cement. Okay, one of the key questions you could ask is, how does the sample preparation look like? So here's a video that one of my students created last year. Again, the process is very similar to how you would prepare a sample for SEM EDS, but in case you're not familiar, here's a video that shows that you essentially make a paste of your cement or epoxy. You cure it, and then you cut it. So you have two, let's say, flat sides. And then polishing is optional. Some of the modern spectrometers and spectrometers, they can actually work on a rough surface, but the polishing does improve the signal quality quite a bit. So I always recommend polishing. And also, if you're going to do SEM on the same area, the polishing is very helpful. Once the spill or this disc is ready, you can put it under the spectrometer and go ahead to collect your data, which you can then classify and get the analysis done. Okay. So we did this on a couple of different systems. So this was some work done on a calcium sulfur illuminator system. Again, we get a very decent agreement between the two techniques. And in fact, what we find is that the read wheel also has some intrinsic uncertainty, and Raman also has that. When you combine them together, they can actually really be beneficial to each other, because the strengths of one can be paired with the weaknesses of other, and together they can increase our confidence in whatever we are quantifying in a given mixture. Again, the approach here is you start with a small area scan, you figure out what are the key phases present, you fuse them together, and then you slowly scale up from there to a larger area where you can then to see what are the phases present. So in this case, for example, we can see that both the polymorphs of GLMI, the orthorhombic and the cubic one, because each has a very unique pattern in the Raman spectrum. Then one of the things we have been very interested in is that can we take one step further? Can we look at the size and the shape distribution of some of these clinker phases? Because we have this high resolution scans, can we then obtain what we call the phase specific particle size distribution? So instead of having one global PSD, we can get a PSD for every single component within that system. And I personally think this is going to be quite interesting moving forward, considering that let's say in the North American market, we have now more and more of the blended cements coming in. So if you have type 1L cement, what is the fineness of the limestone that is being added inside that cement, and what's the ultimate fineness if you co-ground or interground them? And that's going to be quite interesting. Of course, you can look at other things such as the aspect ratio, volume fraction. All of these can be picked up from that size and shape analysis, depending on the resolution you use for your scan. And this work came out a couple of years ago on the cover of JPCC, so I think we were very proud. I think this really starts off this new kind of era of where you can look at both the size and the shape and the quantification on a single material with a single technique. I was trying to actually explain the relevance of these results to my kids, and they really like M&Ms. So I thought, how can I explain them to them? So, there are two ways to imagine cement particles inside two ways to compare them. So you can imagine all the cement particles are equally size and shape and nicely organized, or they are randomly distributed. In the case of cements, it's really towards the latter, where what we then did is we took the individual particle size distribution of each cementitious phase, combined that with the amount, and we came up with this very empirical parameter called the composition size quotient, which we can see is able to predict the 3-day cumulative heat of the cement paste made from these dozen different cements, which means that there is something about considering these individual phase size distributions. Then we have also done this on Raman imaging on the aggregate. This was a project we were looking at how we can quantify different phases present in granitic rocks. And again, if you do both Raman and SEM, again, you get a very high level of confidence in the phases that you are looking at. And this can be very helpful for this, what we call the correlative characterization. Then one of the things we wanted to look at was actually measure expansion that is happening in these aggregates. So the application here was that for this was a grant from the Department of Energy, where we're looking at there's something called radiation-induced volumetric expansion, where as you subject radiation to many minerals in the aggregates, they can expand. For example, quartz can expand by the order of almost 18%, turning into amorphous silica, and that can be quite problematic for nuclear reactors and the biological shield. So one of the things we've been looking at is we did some work where we took samples where we imaged them before sending them for radiation in Los Alamos. We subject them to radiation, bring them back, and then here if you look at now at the same area, we did Raman and SEM, as well as the pre and the post, which represent the height maps. We are able to see what is happening as a function of that radiation. So maybe a question for the audience on this: can anybody notice what is happening if you compare the pre and the post image in terms of the height maps? Is there a particular phase that you can notice which is undergoing some sort of change? Okay, so maybe I will kind of answer this question. Essentially, if you pay close attention to quartz, Alessandra, can you confirm if my laser pointer is visible?
Yes, it's visible.
Okay, so if you look at this quartz phase, first you can confirm that this is indeed quartz, because if you look at the EDS maps, you can see the silicon is very bright and the aluminum is missing here. So you have high confidence that this is indeed a quartz particle. And then if you look at the pre and the post map, you can see in the post map it's actually now glowing, which means its height has increased, which means the quartz has basically expanded. And due to that expansion, some of that quartz has even, let's say, broke out of the sample. And this is exactly now by fusing multiple techniques, you can get phase specific expansion as opposed to getting an average expansion. Now you know which phases are expanding. And then we did this analysis and compare that with some of the modeling approaches. We got some really kind of good results. So this is where I think combining Raman imaging and fusing it with other techniques, this kind of multimodal imaging, I think is the future of characterization. And this is where there's a lot of room to explore new methods and new techniques. Then we have also done look at other things where we track carbonation over time. So we take a sample, we seal it from all the sides, and then we just expose it to CO2 from the top, and we see how the calcium carbonate front is moving inward and calcium hydroxide front is moving back. And we can see clearly there's sort of this diffusion barrier that forms, which ultimately stops that carbonation because the CO2 cannot get further in. So the idea was to kind of create this kind of a movie of carbonation of a sample. And this was the work we did a couple of years ago. But then as a follow-up to this, what we also start looking at is, can we look a little bit deeper into what is happening when this carbonation front is forming? So this work I did with another student, following that early work, we again combine multiple techniques. So we take laser profilometry, we expose the sample to CO2 from the right side, and what you can see is if you image, you have a clear delineation between the calcite front and the portland front. But then what we really want to know is what is happening at this area which is carbonated. And there, what was very interesting, this work was done by my student here, Sudarshan, where if you take a look at the this droplet test where we measure the contact angle variation, and if you place that droplet on the right side versus the left side, we actually see quite a bit of difference. I'm going to maybe play this video again so you can just see it. You can see on the fully carbonated zone, the droplet is not fully absorbed, which we infer as that area being highly dense and of low porosity, which makes sense because that stops the ingress of CO2. Now, from a durability point of view, this is great because we don't want that CO2 front to move. However, if your goal is to actually sequester CO2 and get as much of that CO2 in, then this system is not good. And again, this was a pure OPC system with different SCMs, with different binders and different things. Things could change quite a bit. So again, we get now the full evidence that there's indeed a porosity reduction in this carbonation front based on these methods. We've also been looking at single particles of clays, because one of the issues with clays and calcium clays in general is that their water demand is quite high, and we have to really understand what's happening here. So one of my students, Pablo, here did this kind of very interesting experiment where he isolated single clay particles under two glass slides, and we were able to figure out what's happening. It turns out, if you look at here, kaolinite, it opens up nicely. This exfoliates like these individual, kind of potato chips, and this is kind of well known. But what we find interesting is that even your metakaolin does that to some extent, even though that layered structure has been changed due to the calcination. So what this really means is that it has a lot of internal porosity, which takes in that water and affects water demand. So now we have that evidence by looking at the single particle. Then we are also interested in looking at particles of sand as well as gravel. So here's some work done by one of my students, Baizid here. He came up with this very simple and elegant particle shape metric, PSM, which essentially takes into account different parameters that signify the shape of a fine aggregate. And we took a bunch of sands and we imaged hundreds and hundreds of these particles on a very, let's say, low-cost microscope. And turns out this particle shape metric is actually very well correlated to many different things which we care about in mortar and concrete, all the way from packing coefficient, which comes out independently from helium pygnometry, as well as yield stress, which tells us about workability, as well as the strength and the open porosity. So in general, our key message here is that size is very important, but the shape also matters. And now there is a way to encapsulate that shape into a single metric. Then we go one step further. We define something called the particle packing factor, because one of the things we have been interested is in designing ultra high performance concretes, which can have a strength of 3 to 4 times more than concrete. So if you want this kind of 120, 110 megapascal concrete, you really want low porosity. And for this low porosity, we find the particle packing really has to be done quite well. So we define a factor called the ppf, which can then single-handedly sort of explain this improvement in the strength, and that can be used as a design, somebody to design UHPC to just optimize that ppf value. Finally, for Raman imaging, one of the things we have also been doing the particle analysis is looking at ACerS. So this is some samples we recently obtained. We were interested in looking at where that ACer gel is, and if we can identify it. So if you kind of look from left to right, we're kind of zooming into specific directions here. And one of the things we wanted to do is we really wanted to follow this kind of thin river of the ACer gel that is flowing sort of in the aggregate. And so you can see it's really 50 microns thin, and we wanted to see if we can map this with Raman imaging. And what we find is that if you actually create a hyperspectral image, you can actually start to see the ACer signal quite well. It's actually going through what seems to be a limestone particle, and there's a wetterite particle on the left side. And we can now finally start to map it because the spectra, even though they're broad, there are clear signals for that from the literature. So one of the things I wanted to do is, okay, if we can summarize this issue of looking at ACer with Raman imaging using generative AI. So I showed you a picture of a generative AI image, but here's a full video that I created using the Sora app. So I'm just gonna play it here. I put in a prompt regarding, what happens when you have an engineer who's worried about ACer, and then somebody comes in and proposes Raman imaging as a forensic tool.
Alkali silica reaction got you down? Meet the all-new Raman 3000. With Raman imaging, you can see where that pesky gel is hiding. Spectral fingerprint? It's so clear. Diagnose ACer fast and proud. Fight the gel. Use Raman.
So anyway, I think it's kind of fun to see how far generative AI has come, and I think it's kind of interesting. You can create these 20-second videos, which are pretty funny. I'm looking forward to when we can create like a 2-hour version of some of the things. Okay, I'm going to take a brief pause here, and before I start with reactivity, I want to see if there's any questions on the particle analysis work. And I do see there are 2 questions in the chat, so I'm going to answer them. But if there's other questions, feel free to ask them in the Q&A. Okay, so the first question is from Shikhar. You compared it with SEM, but because it uses visible light, won't have. Yes, indeed. If you compare Raman spectroscopy or Raman imaging with SEM, it does have a worse resolution. The best resolution that you can get with Raman is on the order of 350 nanometers, or just less than half a micron, whereas with SEM you can get a resolution of a few nanometers. So from a resolution point of view, SCM is much better than Raman. Raman is a bit worse because we are just limited by the diffraction of light. But that being said, even with that resolution, considering most of the cementitious particles are micron sized and greater than a few microns, it can still be quite useful. Second question is XRD versus Raman from Tariq. Which technique is best for analyzing crystalline phases, and which is best for amorphous phase? Yeah, I would say, X-ray diffraction is the kind of gold standard, and it's a very well-established technique for analyzing crystalline phases. So this is why we use XRD as a North Star to do our initial calibration and to really see what parameters can be good for Raman to catch some of those crystalline phases. That being said, once this initial work is done for certain systems, then Raman can also be quite helpful and very complementary in analyzing these crystalline phases. Regarding amorphous phases, this question is a bit more complicated, because with X-ray diffraction you can quantify amorphous phases, with reticle refinement and the internal standards, but it is always a little bit complicated because you're looking at an amorphous phase, which is inherently XRD has just a hard time trying to quantify. I would recommend something like NMR would be much more powerful, or X-ray PDF. In terms of Raman can look at amorphous phases, but again, quantifying them is kind of an open challenge. That's something we are looking at, we have been working on. But the nice thing here is with Raman, you do get a unique signal depending on the nature of the amorphous phase. So in principle, if you are able to map them out, you may be able to quantify them in the future, but that's an open challenge. Okay, so I think I don't see any more questions, and the two I have answered. So I'm gonna move on to the next section in interest of time. So let's talk a little bit about reactivity. And this is some work that was done by a couple of my students in the lab who've been working on this test called the UR2, which I'm going to explain in the next few slides. If you consider again from a lighter note about the reactivity, you could have again one person thinking about other women, and the other person is thinking, how can I rapidly predict the performance of SCMs? Can I reduce testing time from days to minutes? Right? We talked about how SCMs are very, very important and integral part of concrete due to many reasons. One of the key issues is that their testing time is a little bit long, and if there's interest if we can reduce that time. This is also important because we are now considering to create what we call engineered SCMs, and for them having real-time quality control is going to be very important. If you consider the reactivity test, there's many animals in the jungle. So there's the SAI test, which is very common and very popular. It's the kind of the gold standard in the industry, and is part of the ASTM standards as well. Then about 10 years ago in EPFL, this R3 test was developed, which was really a game changer. It cut down the testing time from about 28 days to 7 days because it was very well predict that 28-day SAI in a week. And it has, over the past 10 years, received a lot of interest and attention, both in the academic labs as well as the industry. And if you consider SAI as a tortoise, I consider R3 to be here. But what I'm going to talk about in the next few slides is the UR2 test, which was developed in our lab earlier this year. And this reduces testing time even further, takes one step further. It can now predict the R3 test in a matter of 5 minutes. And I've not still figured out what animal I should use for this, but I'm going with the cheetah for now. By the way, I should also mention there's many animals in the jungle. There's many other reactivity tests, and there is a very nice a report from the Federal Highway that you can read from my colleagues here, which do a good survey of this jungle. But for the purpose of this particular talk, I'm going to stick to talking about the UR2 test. Just to give a brief insight on the R3 test, well, the R3 test, you can do it either by the cumulative heat method from the calorimetry, or you can do it with the bound water method. And one of the bound water, this method is now also entered one of the performance-based specification at ASTM, which means there will be a lot more data coming out on this test. The original papers say that you can predict the relative compressive strength of different materials. You may have slightly different slopes depending on the material, but generally the higher heat leads to a higher performing material in terms of its strength. So one of the things we wanted to think about here is that if we can develop something around dissolution, because the basic assumption here is that if something doesn't dissolve, it doesn't react. Then if something dissolves, it will react to some extent in a cementitious system. So what we came out with is very simple method where you just look at dissolution. We don't look at precipitation. So dissolution far from equilibrium, we had a very high liquid to solid ratio. And the main effort has been to kind of figure out empirically under different dissolution conditions at different temperatures, different alkalinities, because we don't want to over dissolve a material, or we also don't want to under dissolve. We just want to dissolve the right amount, which then is empirically linked to the 7-day R3 or the 28-day strength. The other thing, so this idea of using dissolution to predict reactivity actually has been around for several decades. And for us, the main thing has been to identify the right conditions under which the dissolution approach can work in a very, very rapid manner. That is on the order of a few minutes. The other thing is you can measure these concentration of aluminum and silicon using an ICP, but the ICP tends to be a very expensive piece of instrument, can cost anywhere from 200 to 300K, and not everybody has access to it. So we wanted to also figure out low-cost ways to measure these ion concentrations. And there also we look at this very simple colorimetry-based method where you add certain coloring agents, and then you can use a UV vis, which is like a few $1,000s, like say $5,000, or you can use a $30 camera you can buy from Amazon, and you just take a picture of your solution and get the concentrations in a very precise way. You combine these concentrations into what we call a dissolution index, which then turns out can predict the performance reasonably well. Just double clicking on this low-cost camera-based analysis, one thing you have to be careful is you kind of build a calibration curve under control conditions. And once you do that, you can now actually measure concentration at the micromole level, which is on the ppb level. You can now measure aluminum and silicon just with a $30 camera, which I think could be quite useful in places where you don't have access to high-end instrumentation. And we have now done this test on almost 130 unique clay specimens. The paper that came out earlier this year, we had about data of 50 clay specimens. And since then, we have done 80 more. And turns out once we develop that master curve, it starts to become quite general. And those 80 additional samples basically lie on that original master curve. If we compare this, a subset of this data also with the bound water, we actually get a very decent correlation. So we are very kind of excited by these results that now in 5 minutes, you can predict the reactivity of these clays. Now our next target is looking at other SCMs such as fly ashes and natural pozzolans and maybe slags. And we're seeing early promising results for fly ashes. And I hope I can share some of that data sometime next year. But I think the main idea here has been to really identify the conditions under which we dissolve these things. And of course, the other important thing is the correlation between the UR2, the 5-minute test, and the strength. And here also, if you look at the 28-day strength of mortars made with cement replaced with, let's say, 20% of calcine clays, we again see a very decent correlation. And also on the strength activity index test, we also see a correlation where you can now predict that SCI value reasonably well. One thing to keep in mind here is that very important is that we cast these systems at both a constant water to binder ratio as well as a constant flow. So it's kind of, we are taking the European approach as well as the American approach. So we call it the mid-Atlantic standard, because if you don't do both of them, then you can run into a lot of issues, because some of these materials with very high strengths also can have very high water demand. So you have to be very careful how you cast these mixers. So in the future, what we are thinking is that, while the 5-minute test is kind of very fast and very, very helpful, it does require some of the manual wet chemistry, which can require some effort to do. And one thing we have been thinking about is, if you make a fully automated version for this, then somebody could use it as a benchtop device, just drop the sample in 5 minutes. It's kind of like a coffee machine. It does the whole analysis for you, all the dilution, dissolution, filtration, and then you get the result. In addition, then you could add to an actual clay calcination plant or any kind of plant which is producing some sort of engineered SCM, where you want real-time data on, okay, what's the quality of the material that you're making, and that can be quite helpful. On that note, I'm going to take a pause here also on the reactivity section if there's any questions before we go into sorptivity.
I think there's a question from Roberto. Can you please expand on the calibration? How do you compare colors?
Yeah, indeed. The calibration for the colors, this is very straightforward. If you actually go online and look at our paper that came out this summer, we have the entire Python code shared. But essentially, for each of these images that you take for the cuvette, you can extract an RGB value from the Python code, and that RGB value, then you assign an average of that to the actual concentration on known standards. And once you build that calibration curve of known standards and the RGB values, you have a curve. And then in the future, now you can just take a picture of a new sample and it will fall somewhere on that curve, and then you know what the concentration is. And you can use your ground truth to be ICP or VVIS, whichever is already verified, and then this camera method can work. One thing you should be very careful is that your lighting condition, your camera itself, all of these things you have to be a little bit careful about, because if you're not, this can be sensitive and your numbers can change. So you have to be careful. I would recommend being in a consistent lighting condition and having the same camera to do this.
Another question I have, so all this work have been done in clays. I think I understand it's like related to calcine clays. Is this like work can also expand to other supplementary cementitious material as well?
Yeah, indeed. And that's what we're actively working on right now. My lab has about 400 unique SCMs sitting in my basement. So we are slowly, working through them. But the idea is that we have now tested this on about 60 fly ashes, and we are seeing some promising results. And then the idea would be to also take this to large data sets of natural pozzolans, slags. So I'd also say that if anybody here wants to collaborate and has access to different SCMs, feel free to send me an email and we can collaborate and chat, because I think for almost all SCMs, because they all rely on the pozzolanic reaction and we care about the aluminum and silicon, we can work on that.
Thank you. There is also a question from Juliana. Some phases are more sensitive to temperature than others. How do you account for this in a test run at 90°C?
This is a great question, right? And this is the whole goes to the whole assumption of this test, right? So the reason we have this kind of very aggressive condition is just to try to accelerate of that dissolution. Now, some phases will dissolve more, some phases will dissolve less. But for us, what we are then really doing is, for example, calcine clays, we catch them at 5 minutes. For another material, for example, fly ashes, we're actually seeing maybe 15 minutes is better than 5 minutes because it's a little bit slowly reacting. So the time may be changed, but somebody could even change the temperature or the alkalinity. But the whole idea is you can play with all these different things. The end goal, it really depends on what you're trying to predict. For us, we're trying to predict the R3 as well as the SCI. And for us, then, it's just an optimization game of where we catch. So we change the time, but we keep the dissolution conditions constant, because that's what has been working for us so far.
We also have another question for Tariq. What causes fluorescence in ramen?
Yeah, so fluorescence is a very kind of a problematic thing that happens in ramen, and this is something we never want to have. Essentially, you have these fluorophores in the sample. This could be sometimes organic impurities or some of these iron containing phases, and they basically fluoresce, just like you have this X-ray fluorescence, and that fluorescence basically basically saturates your detector. It comes up as a huge signal, which is basically like a big hump, and all your true peaks are hidden. And every time that happens, essentially, you cannot get reliable signals. So I think in order to really prevent that or avoid that, there's many strategies that are out there in the literature. I think one of the ones that we have tried in the past is something called photo bleaching, where you basically use a laser to kind of get rid of those fluorophores, kind of burn them out. You bleach them with photons, and after that, the fluorescence actually decreases in some of these ashes we have looked at. So that will be one way to do that. Yeah, there's also a question about how the software can. Indeed, there are software where you can just do an automated correction if you can sort of see where that band is, and that, depending on what kind of instrument you have, that can also be done. Okay, all right. So if there's no more questions, I'm gonna continue and talk about the last part here, which is the sorptivity part. So the sorptivity work, this was started with my second PhD student, Hossein, who also graduated this year. And the idea here was looking at some of the durability of cementitious systems. If you consider from a durability point of view, so here's an example here, a kind of unfortunate disaster that happened a couple of years ago in Florida, where you had this entire part of the condo collapse overnight. Nearly 100 lives were lost. And one of the potential causes of failure in this is considered the corrosion of the reinforced concrete in that system. Now, this is still actively under investigation by NIST, but if you actually go to their website and see what they're doing, one of the key tests they're doing is looking at the sorptivity of these systems, because ultimately how much water that goes through concrete and reaches the rebar is a huge decider in how much corrosion there will happen. So if you look at the transport properties, there's many many different things of interest here, but what we care about is the absorption or the sorptivity, which we can define as follows, right? Essentially is the ability of these materials to absorb water and transport water through capillary action. Now, there is a very nice standard, ASTM standard, for these sorptivity measurements. However, it's a little bit time consuming and labor intensive. Essentially, you have this specimen which you expose to water from one end, and you repeatedly measure its weight over time to build this kind of penetration curve of the slope of which can help us tell us how rapid the water is moving in. So here's a little video of that test done on cementitious paste samples. Again, this is a very sped up video, and then it takes quite a bit of time to do this test. So initially, when we start doing it, my student and we were talking, and it was like, this is a very, very painful and laborious test. Can we try to accelerate or automate this test? And of course, you have to do this on mortar and concrete as well, and the measurement can continue for many days. So one of the things we thought about is, why not we consider some of these computer vision based methods to try to automate this. By the way, there has been some approaches in the past where people use in kind of an automated balance to measure the weight change as the water is taken in. However, there has been some complications regarding the buoyancy that can change as the water is absorbed, as well as not everybody has access to this kind of an automated balance. So what we thought of was the two methods. One is the droplet method, and the other is the waterfront method, where the idea is to really first place a droplet and see how much absorption happens. And then the second is really looking at the waterfront itself as it's moving through the sample. So let's start one by one. Let's start at the droplet method. So here I'm going to show a small video where you have 3 samples of different sorptivities, and when you place a droplet on it, let's see what kind of response we get. So you can see that here from left to right, you have different responses in how the droplet is being absorbed in the surface. And in fact, if you look at the one on the left side, you can see here, you can see the lights in the middle, as well as you can see the upside down view of my lab, because this is the floor slab at the top. So now you have a mini tour of the Garg Group's lab. But if you want a full tour, of course, you should contact me and visit us sometime. But the idea here is that can we use this droplet to get some idea on the sorptivity of that system? So the first thing here is we need to do these contact angle measurements, and this I guess everybody is well aware of. Depending on that, how big or small that angle is, we can define how wettable the system is. So one of the key things we wanted to do here was that we are looking at using this goniometer in our shared facilities, and we were actually spending quite a bit of money. We were paying about $20 an hour to just use this equipment. And then, as we were talking to my student, like, what is there in this instrument? All you have is a light source and a pipette and a stage and a nice camera. And why can't we just build it on our own? So my student was kind of very good, and so he went ahead and built this kind of a very cheap goniometer for like less than $200. We bought all the parts from Amazon. And essentially, we actually even have 2 cameras looking at the sample in orthogonal fashion, so you can get 2 data points on that droplet as it being dropped. And the nice thing about this system is we made the algorithm open source as well as the data set, so you can now use it anywhere, and it can now in real time predict the contact angle after it was trained on a large number of images. And this work has now got some good attention, and I think this is kind of paves the way for building these kind of very low cost and open source equipment for laboratory usage. Then we wanted to see, can these droplets actually help us understand this initial sorptivity, which takes several hours to measure? Turns out when we measure a range of mixes with different water cementations at different curing times, we find that the contact angle actually has some correlation with that initial sorptivity. In fact, when we also correlate the different parameters of the droplet dynamics with that sorptivity, we actually find some very interesting correlations. So here's a small video that we put together, which shows how the drop volume and its change very well is in alignment with the sorptivity of the sample. From left to right, you have samples of increasing sorptivity, and you can see the droplet dynamics changes quite a bit. Again, here's another snapshot where we can see just in a few seconds, even before you actually officially drop the droplet starts to be sucked in by the substrate, because it's kind of hungry for that droplet. Okay, so that was the droplet method. The other one is the waterfront method. Here we said, okay, instead of, while the droplet method is great, it's really kind of interesting method, there are some shortcomings. One, it is that is mostly limited to the surface of the sample. The second is that it is currently mostly work on the paste sample. So if you want to go to mortar or concrete to kind of scale it up, we do need to do something else. So I've been thinking about this waterfront method. The literature is full of these images where the water is rising up in the sample, and we thought, why not quantify this increase and train a machine learning computer vision model, which is then paired up with the sorptivity data. And this is exactly what we did. And my student also actually made some Illinois logo blocks just to kind of have some fun with it. And what we're able to do here is that with this approach, we're actually able to see in real time, again, that waterfront as the sample is absorbing water. Now, these are highly sped up videos. This process takes maybe several hours to several days. And by doing this, now we can actually measure this water ingress very, very frequently, almost in an automated way. You can record a video over several days if you want, as opposed to using a human, which is only going to take certain weight measurements. And again, if you look at across a variety of samples, you can see that. Let me see if this video plays. You can see how from left to right, as the sorptivity is changing, you can see the slope of the line is also different because the rate at which the water goes in is quite different. One of the questions here is, why does the wetted region actually looks darker? Well, the reason is now as the pores which are filled with air, they get filled with water, the refractive index changes, and that allows us to basically see, whatever you can see with your eyes, you can also then catch it with the cameras, and then you can train a model on it to quantify that water uptake. So again, highly sped up video, but you can nicely see concrete is basically like a sponge, is sucking up water, right? And now if you want to make good concrete, we really want to have it not behave like a sponge. It should really be as impermeable as possible, because then your rebar is then protected from whatever ingress, whether it's water, chlorides, sulfate, anything that is protected from that transport. Again, you can build a very simple setup where you have adequate lighting and cameras to look at this process in real time. And I can imagine in the future one could do this on dozens and dozens of these samples. You can put them in rows, put cameras, and let this test run. You go home on the weekend, and a week later, everything is done in an automated way. And you can qualify now new materials, new kind of systems without doing the other painful sorptivity testing. As I said, you can scale this to mortar and concrete. Again, you can measure these area ratios over time. Finally, this work is fully available online as an open source code. So you can go online, you can scan this QR code. So all you need to do is in your lab, then you just set up your own camera, your own samples, and you can run this test as well. So here's a little video that my student put together for summarizing this work, and here it goes. Okay, so just to kind of summarize the things that I've talked about so far, and I will take questions also on the sorptivity section at the very end. For particle analysis, I think Raman imaging can be quite powerful and useful tool for phase quantification. When combined with other techniques such as SCM, as well as others such as profilometry and optical imaging, we can actually get this very comprehensive and rapid analysis in just a matter of few hours, which can then predict long-term performance. For reactivity, this new UR2 test that I've presented today, they can predict the long-term 7-day and 28-day performance parameters in a matter of 5 minutes, which means that now you can rapidly screen a large pit of any kind of SCM. That could be a quarry of a natural pozzolan, or it could be an ash pit. You can build a 3D block model of what's the quality of that metal in that large pit, as well as you can also do this real-time quality control. You can figure out what temperature to calcine your material, how much to grind the material, because you have this real-time feedback on the reactivity of that system. And finally, for the sorptivity, with using these computer vision methods, now it is possible to accelerate and automate these durability measurements, where we can get results on the order of minutes, even down to seconds. So there's a bunch of papers that have come out over the past few years that you can find online. If you cannot find, if you are not able to access, just drop me an email or reach out to one of my students on LinkedIn. I'll be happy to share. And there's many more that I can't fit on this slide. With that, I want to really thank my students and my research group who has been instrumental in doing this work. These are my students who are currently with me, but there's many who have graduated whose work I showed. So I've been very, very lucky and fortunate to have these very good students who have been working on these topics that I talk about today. And finally, thank you all for listening. And if you want a copy of these slides, you're welcome to scan this QR code and you can download these slides so you have them and you can see them later on. Thank you so much, everyone.
Thank you so much. And thank you so much, Professor Nishant, for this amazing talk. This was very great. For everyone here, make sure you respond to the survey after this talk. And I want to share again my screen real quick. And remind you guys that we're going to have our next speaker, Cesar Romano, Senior Researcher of the Department of Civil Construction Engineer at the University of São Paulo on February 3rd, 2026 at 1 p.m. He will make a presentation from rheological requirements to aqua-efficient mix design in 3D printed cement-based materials. Also, I want to remind you guys again about the upcoming Cement Division ACerS meeting, the 16 Advancing Cement-Based Materials, June 10 to 12, 2026, at the University of Miami, Coral Gables. I hope to see you all. Thank you so much again, Professor Nishant, and thank you everyone here to be in this webinar. So yeah, let me stop this. Yeah, can you stop? Yeah, okay.